Hi, my name is Jason Harlow. Welcome to my V Office Hour. I'm going to go over Physics 132 H1F Fall 2009 Test 2 Problem 4. This is a question based on Knight 2nd edition Chapter 30 on potential and field. Particularly this is on section 30.5 capacitance and capacitors, and in particular combinations of capacitors. Capacitors can be wired in parallel or in series. So we're going to go through a little circuit that has some of both. So first, let's carefully read through the question. Consider the combination of capacitors shown in the diagram, where C1 is 5 microfarads, C2 is 1 microfarad, C3 is 2 microfarads, and C4 is 3 microfarads. Find the equivalent capacitance of the network of capacitors, all listed in microfarads here. And here's a nice diagram just showing a portion of a circuit, which a wire comes from the left, encounters C1, then splits to go to C2, and then splits again to go to C3 and C4, and then recombines on the right. Okay, so there's equation 30.21 on page 925, which is the capacitance for a bunch of capacitors all hooked in parallel. It's just the total capacitance is the sum of all the individual capacitances, parallel capacitors. And then you can go on to page 926, series capacitors. When you hook capacitors in series, the equivalent capacitance is the sum of all the reciprocals, and then you take the reciprocal. So let's take a look at my solution. Okay, so taking a look at the solution for this one, even though the diagram looks a little confusing with all these different junctions, what you need to recognize for this is that if you have these capacitors 2, 3, and 4, and they're hooked up like this, and there's current coming through, it has to choose either to go up through 2, or down along this path through 3, or down along this path through 4. And then it's going to always come back and recombine to go out the same way. So this circuit is equivalent to this. Still, the current has to do the same thing. It comes up, it either has to go through 2, or go down here and then choose to go through 3 or 4, and then come out this side. So this is equivalent to this, and it doesn't matter where the junction is. Again, same thing, it's equivalent to here. The current comes in, it splits up 3 possible ways, going through 2, 3, or 4, and then ends up here. So all 3 of these circuits are just different ways of writing the same thing, meaning that these 3 capacitors are in parallel. So there's an equation, equivalent capacitance for 3 capacitors in parallels. You just add them. Here we're adding 1 plus 2 plus 3 microfarads equals 6 microfarads. So that part of the circuit is 6 microfarads, and now that's in series with C1. So the way to find equivalent capacitance for 2 resistors in series is to add the reciprocals and take the power to the -1. And we find that it's 1 over 5 microfarads plus 1 over 6 microfarads, all to the power -1. We get 2.73 microfarads, which is closest to answer B. Okay, so the equivalent capacitance, 2.7, is somewhere in the mid-range of all these individual capacitors. One of the things that's interesting to note, so a capacitance measures how much charge is stored in a capacitor given a particular voltage. So if you have capacitors in parallel, they all have the same voltage drop across them, but each of them hold charge. So the capacity of all these capacitors to hold charge is increased when you hook them in parallel. You just sum them all up. But when you hook these 2 capacitors in series, like we do for the second part of the problem, you have 1 voltage drop, and then the charge is shared over these 2 capacitors in series. So the amount of charge, total amount of charge, is less, so the capacitance of two capacitors in series is always less than either of the individual capacitors. So we ended up going down with a 5 and a 6 down to 2.7. So my name is Jason Harlow, and I proved this message.